Hello students, welcome to the class of Digital Signal Processing. Today we will be discussing the final value theorem of Z transform, and then we will be doing some numericals on the initial and the final value theorem. So these numericals are very important because this topic is asked regularly in your exams. Let's get started. Okay, so first of all, let's do the proving of this final value theorem, and then we will do the numericals. So proving is not very important, but yes, it can come. So the final value theorem of the Z transform says that final value theorem. The statement of final value theorem is that. So what do you mean by final value theorem? What should be the value at x of infinity? This is the condition that without knowing the exact value at the last point, you are trying to say in some way that what is the value at x of infinity. So what they say that if xz is the Z transform of x of n, and if it is positive sided, you can say that the signal is positive sided, then ROC and the ROC, the conditions are very important. The ROC of xz includes unit circle, or you can say includes mod z greater than 1, and z to z minus 1 into x of z has no poles on or outside the, has no poles on or outside the unit circle. Only in that case. What are the conditions? First, let us see the conditions once more. This condition simply says that if the Z transform of xn is x of z, and the ROC includes mod z greater than 1, it can be anything other than that, but it should be mod z greater than 1. Includes but is not necessarily confined. That means it can be something else also. Here the statement I will put it over here, but not necessarily confined. Means it can be, it has to include mod z greater than 1, but not only that much. Fine. And second thing is that z minus 1 into x of z. If you multiply this xz with z minus 1, and after that there is no poles on the unit circle or outside the unit circle, then we can say that x of infinity is equal to limit z tending to 1, z minus 1 into x of z, x plus z. This is a one-sided, right-sided Z transform. Okay, let's go through the proof very quickly, and then with the questions, this one will be becoming more clear how you need to use it. So see, in this you have to remember that if you take the Z transform of x of n plus 1 and subtract it with the Z transform of x of n, you can write this thing as limit k tending to infinity, n is equals to 0 to a x of n plus 1 minus x of n z to the power minus n. Fine. Now this k is tending to infinity just because we are giving it a name, the infinity a variable. Now in this part with the time shifting property, you can write z to the power 1 into xz. If the z transform we are taking as x plus z, we have to write it in this way, minus z into x of 0. If the initial value is something x of 0, that's why we are writing it z into x of 0, minus x plus z. This will be written as the same thing over here, limit k tending to infinity, n is equals to 0 to infinity. Here we have made infinity as k. So this xn plus 1 minus xn z to the power minus. Now, you can club this first one and the third one to write it this thing, minus z into x of 0. And this side, the same thing remains. So, if you tell that limit z tending to 1, if you make this limit z tending to 1, then limit z tending to 1, z minus 1, x plus z minus z, x of 0, then what will happen? Here you can write this one as limit k tending to infinity. The first one will be x1 minus x0. Then the second one is going to be, you take the summation of this and then write it. Then the second one is going to be x of 2 minus x of 1. How we are writing this thing? So first we are taking the value of n0, then we are taking the value of n1. This way we are going. Fine. Here if you take the value of n0, it will be 1, it will be 0. Then at the next step, you took the value of n1, 1 plus 1, 2, and then here it is 1. So this way we are going ahead. The last one that you will get over here is going to be x of k plus 1 minus x of k. K plus 1 minus x of k. X of k plus 1 minus x of. Fine. So finally what you can write this is x, the things that are going to remain over here, that you have to see. See, x1, x minus 1, all these are going to get cancelled. So the only thing that is going to remain over here is x of infinity into x of 0. X of infinity minus x of 0. This 0 won't be getting cancelled from anyone. And over here, this k is tending to infinity. So x of infinity minus x of 0. This is going to remain to over here, limit k tending to infinity. If you take, therefore, if you take this x of infinity, and this side it is limit z tending to 1, z minus 1 into x plus z minus z into x of 0. So this x of 0, okay, I'll just rewrite it. It is basically becoming over here limit z tending to 1, z minus 1 into x plus z minus z into x of 0 is equal to limit k tending to infinity, x of infinity minus x of 0. Now, this x of 0 will get cancelled since z is equal to 1. Since this one is equal to 1, so it becomes limit z tending to 1, z minus 1, x plus z minus x of 0. And this side limit k tending to infinity, z infinity minus x0. So this two gets cancelled, and finally you have limit k tending to infinity over here, this side. So you can write it as this one as x of infinity. Sorry, here it was x. So here you can write it x of infinity is equal to limit z tending to 1, z minus 1 into x. Okay, now let's do some problems so that you understand it on the final value theorem property and the initial value. So let's go on and do ahead first the final value property. The other one we will do when we are doing the other numericals together with that. So they are asking you find x of infinity if x of z is given as z plus 2 divided by z minus 0.8 whole square. So first thing is that you have to inspect the ROC. So ROC for this is going to be mod z greater than 0.8, right? You divide it by z and then see it 0.8 z inverse, 0.z inverse, that will make it z mod z greater than 0.8. And if you see the other condition, that is z minus 1 into x of z, there is no poles on or outside the unit circle because this is your 0.8. The pole is over here at 0.8. On or outside the unit circle, there is no pole. There is a pole inside the units z minus 1 into x of z. So we can use the final value property. What it says that x of infinity is equal to limit z tending to 1, z minus 1 into xz. Just do it, z plus 2 by z minus 0.8. Put the value of z equal to 1 everywhere. So what you are going to get is equal to 0. So the final value is 0, x infinity. Now let us go ahead and see a question where there is a pole lying there. So in the question, find x of infinity. Find x of infinity if xz is equal to 3z plus 4 by z minus 1 divided by z minus 1 into z plus 1. Here, if you multiply z minus 1 into x of z, what you get is z minus 1 into 3z plus 4 by z minus 1 into z plus 1. So this z minus 1 gets cancelled. Now, if you write it, it is going to be limit z tending to 1. This one was limit z tending to 1. 3z plus 4 by z minus 1. Now, there is a pole. Z is equal to 1 is a pole. And this pole is on the unit circle. Pole, and this is on the unit circle. This is on unit circle. So in this case, x in infinity is not defined. We'll be doing more problems on this in our next class. So thank you for today. Practice all the properties and the examples, whatever is discussed with this. We will be doing a complete numerical session on all the properties. That will be helpful. Please go through that. The next video will be about that. Thank you.